Yeah, it is given.
No. But
I did not.
Okay. 1 minute. You keep it ready. Yes, that's what I like.
yes, sir, it's given.
Ganesh, it is given. You check it once. Yeah. Just a little bit. Don't open. Okay. Second session. Good afternoon, one and all. Today we have with us Dr. Ganesh Kumar sir. As for our schedule, actually, it will be Veeresh Babu. Even with the last minute, our Ganesh sir is ready to share his valuable ideas for our FDP. For that, I am very much thankful to you, sir. Dr. Ganesh Kumar is an associate professor in Kakatiya Institute of Technology. He did his PhD from IIT Warangal in the year of 2013. He did his MTech or ME in Birru Institute of Technology, Bitspilani branch, and he did his BTech from Nagarjuna University. His area of interests are thermal engineering, heat transfer, mixed convection, and thermoelectric generators, computational fluid dynamics, thermoelectric generators, etc. He has vast experience of 18 years of teaching experience and 1 year industrial experience. He worked at NIT Warangal from 2002 to 2004. He also worked in SR Engineering College from 2004 to 2008 and joined KITS Warangal, and now he is in KITS Warangal as associate professor. Granted funding from UGC under minor research projects for an amount of 2.5 lakhs. Title is Experimental Investigation on Performance Parameters of Thermoelectric Generators in Spark Ignition System. He is involved in Indo-American Artificial Heart Project in collaboration with the University of Pittsburgh Medical Gender from 2016 to till date. A total 34 publications, of which 14 international journals, 18 international conferences, and 2 national conferences. Registered for 2 Indian patents, supervising 2 research scholars for the doctoral program under Kakatiya University. Published one textbook on 3-vane small-scale wind turbine for domestic purpose. Acting as a member of Board of Studies of KITS Warangal, visited USA for 2 times to present paper in annual conference on American Society for Internal Organs during 2007 and 2018. Delivered guest lecture at various institutes like BITS Filani, Hyderabad campus, Symposium of IIHP, USA, Kakatiya University, etc. Acted as a convener for the total of 5 workshops and FDPs conducted at the institute and university level. Established KITS Indo-American Artificial Heart Project, laboratory in the Department of Mechanical Engineering, and also established various labs in SREC. He is acting as a faculty in charge for R&D cell, and different capacities in the department. So, with this brief discussion, I welcome you, Dr.Ch Ganesh Kumar sir, for his presentation on an overview computational methods in thermal engineering. I welcome you, sir. I am now handing the session to our beloved colleague, Dr.Ch Ganesh Kumar sir. Sir, session is yours, sir.
Thank you, Samir. Thank you very much.
Thank you, sir.
Is it audible?
Yes, sir.
Yeah. So today, good afternoon to all of you. And I'm now going to discuss about, and for this session, we are going to discuss about an overview of on competition methods in thermal engineering. Yeah.
Teachers.
The outline, or keeping in view of the junior faculty as well as senior faculty, I'm going to discuss a brief session, take this session, considering or taking into consideration the introduction to computational methods, steps in simulating model, numerical methods, discretization, applications. And here I'm going to again discuss various problems pertaining to computational fluid dynamics, as one problem based on the fundamental research and other based on the application research. First of all, we should understand why the competition is required. As we know already that nowadays the computational methods has become very, very important, and very exhaustive studies or exhaustive works are going on computational studies. Because the main reason for this is making or conducting a laboratory experiments and taking is very costly, time consuming, and sometimes it was impossible. Hence, the methods are used to optimize statistical soundness, and it is used to study heavy systems for which theory is hard and make numerical simulations. You can see nowadays whatever the application from whichever use, wherever you use, whether it is domestic or industry, always you can see the applications are pertaining to purely mechatronic components. A simple fan, now in olden days it was a mechanical component, but now we can see it is a mechatronic, it has become a mechatronic components. And almost we should know that all the engineers has to come together, and they are doing wonders in this world. So from this I can say that only mechanical engineering singly cannot do any project by himself. An interdisciplinary is required for studies or making any product in this world. Hence, this computational method is also one of the methods where it brings all the engineers together and make the wonders. And you can see here the mechanical way or to whom these computational methods is useful. I can say that it is useful to all the engineers. Coming or concentrating mainly on mechanical engineers, you can see it is used for designing an automobile parts. A simple automobile parts consists of nearly 3,000 parts, and almost 40 to 50% of the parts are mechatronics. And the main problem with this mechanical engineering automobile is the heating or the heat generation. And the heat dissipation has become one of the greatest challenge in this world, not only in mechanical automobiles, but also in aircrafts. And also it has become more challenging in electronic components. And these mechanical engineers will come into picture where we need to decrease the heat, dissipate the heat generated in the systems as much as possible to increase the life of the component. And you can see for civil engineers also, the computational methods is used to maximize the quality of building construction materials, to design fluid pipes, etc. For petroleum engineers also it is suitable to devise optimal oil recovery strategies. For chemical engineers, it is used to maximize the coming to surgeons. You can see nowadays total medical research is playing a very important role, and almost all the medical applications are mechanical and electronic applications. Like if you take a simple ECG machine, in olden days it was a mechanical, but nowadays again it has become a mechatronic component. So all the engineers has to come together so that we can do miracles. Here, why should we go for a competition? We have already seen. Now, these are some of the significant applications which have become successful, where the competition methods were used to design and manufacture and test and implement. Like for example, this is a missiles and this is an aeroplane or aircraft, car which is undergoing a drag force, and this is a weapon vehicle. What is the difference between a computational method, or what are the advantages or limitations of a competition as well as experimentation? The main advantage of competition is we can test more than one quantity at a time, whereas for experimentation, only one quantity at a time can be tested. In case of experimentation, we can generate very less data, whereas in case of computational methods, almost all desired quantities is possible if the coding is performed, if you are expert in coding. And similarly, in the lab session, we can have only one or two models, whereas in the actual or flow model can be obtained in computational methods. And it can obtain limited range of operating. The operating conditions are limited in case of experimentation, whereas there is no limitation for operating conditions in case of computation. The main disadvantage of errors that are occurring here is competition methods is modeling and iteration and implementation. So whenever you do a modeling, you should take care the modeling, you should understand the basic concept or formulate the problem, define the problem, sit with the analysis person, and then you have to do. Otherwise, there will be a lot of problems in getting the errors. And coming to the sources of errors in experimentation is measurements, probe errors, etc. And whoever deals with the computational methods or the computational field problems, they have to come across all these. These are the steps where we need to forego or undergo whenever we do the simulation model. The first one is problem formulation, and the second one is geometric modeling, defining the computational domain, specifying initial and final boundary conditions, grid generation, set up the simulation, CFD simulation, perform and monitor the simulation, examine and process the results, post-processing and generation of reports. So here we are going to discuss about all these 10 points or 11 points in detail for the next part. In order to explain the concept of flow problem, I am taking here, or the CFD procedure, I am taking here a small example. You can see the figure. This is nothing but a aerofoil, which is used in aircrafts. And here I have taken showing a simple figures where in order to explain the concept of or the procedure of CFD. Okay. First of all, you should know what is CFD, what is the objective. You have to define the objective. What are the input parameters? What are the output parameters you need? What is the geometry? Okay, you have to define and formulate the problem. And this definition and formulation of the problem is the first step, where you should sit together with all the engineers and decide the component. Otherwise, you are not going to get the better results. So, formulation plays an important role whenever you start doing the CFD analysis or CFD modeling. And here the parameters, first of all, you should know what are the parameters, which are input parameters, what are the output parameters, what are the fixed parameters, variables, etc. to be defined in detail in this particular problem. Otherwise, you will not be able to get the good results, and the results are of waste of quality. generally we should select the based upon formulation, we should select, there are many analysis methods, we should select the best suited method for us based upon the problem parameters, etc. On the geometric modeling, this is another very important technique which we need to take care of while making the competition. We should understand what are the geometric features of a component which we are going to design or manufacture or do analysis. Like for example, leading edge, trailing edge, curvature, okay, what is the shape, size, dimensions, etc. to be defined well in advance in order to design. And we should select the simplest or optimistic method to model the geometry. For that, you should understand all the models which are available, geometrical models which are available in the market. And we should understand the computational format of the geometry which is suitable for our problem. Like for example, CAD file, which is where you can file, you can make a CAD file in Kakatiya or ANSYS or else SolidWorks, Pro-E, etc. Once the model is the CAD model platform is decided, you should select an appropriate domain. This is very, very important in case of CFD, defining the CFD model. You can see this, there is a figure where you are having a wing that is nothing but a aerofoil plate, and the lines which are shown here are all nothing but a domain which is selected for this particular component, because this wing is going to face a drag forces in all directions when it is flying in the sky. So this is a very simple example like that. You should define your own domain based upon the application, and this domain changes based upon the application whichever you are considering. And you can see the domain can be a body or a fluid flow or a surface. Body is nothing but the part, and a fluid flow where you are going to have effect of fluid particles on the part, the pressure that is being induced in the part due to drag force, which depends upon the fluid particles. And the fluid particles depends upon various parameters like velocity, viscosity, etc. And also we need to model the geometry of the domain computationally using CAD files, and then shape the model, and then extend the domain depending upon the choice on boundary conditions. So the boundary conditions are to be defined by yourself. You have to define your own domain, okay, and you have to check which is the existing domain, which is the virtual domain, and based upon that you have to divide this domain into number of zones in order to make yourself run the program easy way. Once the domain is generated or decided, you need to go for the generation of grid. The grid consists of finite volume cells on which the CFD equations are nothing but, we generally use Navier-Stokes equations, which are nothing but the fluid flow equations. And these are approximated on the fluid finite volume cells. And the fluid domain or the flow domain is divided into number of zones in order to make ourselves simplify the grid generation and reduce the memory requirement and divide the grid for parallel computation. And the selection of grids, here you should remember that the selection of grids is very important. That is, it can be structured or unstructured. To generate the structured grids, we are having a lot of software packages like grid generation, ISM, CFD, VGrid, etc. Whereas for unstructured grids, you need to make your own model, you need to make your own software, and you need to make your own analysis and results. And here we are going to discuss both examples. One is with respect to structured grids and the other one with respect to unstructured grids. And once we make the grid generation is performed, then we need to specify the initial conditions as well as the boundary conditions. Initial conditions is nothing but like fluid flow is uniform or varying, or is the free stream, is the auxiliary program. If it is a unstructured grid, you have to make your own auxiliary program in order to increase the convergence. and specifying the boundary conditions. Once the initial condition is defined, like for example, the time is given at t is equal to 0, like, okay. Similarly, t of t is taken as 0. Similarly, here also we should specify various boundary conditions for the given model. Like for example, the no slip condition, IMSO or OTSO, or zone to zone boundaries. Once the boundary conditions are specified, you have to establish the input parameters as well as the output parameters which are to be considered in order to do the analysis. Generally, once these input parameters and output parameters are decided, we need to define the governing equations of each node. And these governing equations can be directly be used, established in CFD fluent model, whereas if you take the unstructured grids, we need to have our own governing equations, and we need to convert these governing equations into algebraic form. And there are different methods to convert this governing equations into algebraic form, like numerical methods. These are nothing but the numerical methods, okay, like central or forward or backward difference method, Rangi-Kutta method, Lagrangian 2-point, Lagrangian 3-point. Like this, various methods, mathematical methods are available to convert these governing equations of the field flow equations or the governing equations of the surface into numerical algebraic equations. Once these equations are converted, a simulation model can be prepared based upon the batch processing and distributed processing. I have already told we need to convert the governing equations into the algebraic form. To convert these governing equations into algebraic form, we need to use numerical methods. And the numerical methods which we are considering here are finite difference, finite element, and finite volume methods are the three methods which are generally available nowadays. Most of them are using these three methods in order to solve any type of computational problem in this analysis. If you discuss about the finite difference method, you can see it is a robust and simple concept, easy to parallelize and regular bits. And here these finite differences are used for a one-dimensional or two-dimensional analysis for elements. And generally this is used for the applications such as time-dependent partial differential equations, seismic wave propagation, geophysical fluid dynamics, Maxwell's equations, ground penetrating radar. Whereas the finite volume is another type of numerical method, which is again same nearer to finite difference or extension to finite difference, we can say, where it is also a robust, simple concept. But in contrast to finite difference, here we can do the analysis for both types of structured as well as unstructured, or regular as well as irregular grids. That is the flexibility which we have when we go for finite volume method over the finite difference method. And here also it is also used for whatever the applications we use for finite difference, all the applications can be done in finite volume. In addition, it is most suitable for fluid dynamics. And coming to finite element method, here we are not going to discuss much about this, but still we can say this is suitable for designing the machine devices, and it is suitable for the most critical problems and complex problems, static and time-dependent partial differential equations, and geophysical fluid dynamics, seismic wave propagation, etc. So once we establish the input parameters, once we define the governing equations, we need to establish these governing equations onto various, convert these governing equations into numerical methods as well. So in order to understand I have already told this numerical, it is to convert it into new algebraic form. We use these three methods, and the first method is nothing but finite difference method. The most easiest way to convert the algebraic governing equations into algebraic is forward difference, backward difference, and central difference. You might have studied this in your intermediate or BTech level mathematics, which is a very simple way to convert the governing equations into algebraic form. You can see this is a type of grid. The center one is ij, then the right side is taken as I plus 1 x direction, comma j. Left side it is, on the top it is I comma j plus 1, and the bottom it is I comma j minus 1. These are the surrounding elements to the element I comma j. If I want to define, or if I want to do analysis, or if I want to impose the governing equations or the onto the element ij, I will define this with respect to the succeeding or preceding or top or bottom elements. So for example, if it is a backward difference, we define this ij with respect to I minus 1 comma j. If it is forward, we take this I plus 1 as an element. If it is center, ij will be the center, and it will be defined with respect to the left element and the right element. And these are the expressions which we use to find out, which you have already studied, to find out the properties of an element. As you can see, this is only a first order differential. If you want to go for the second order derivative, we again do the analysis. Then we get this, for central difference, we get this is the equation. Whether it is central or forward or backward, the equation doesn't change. And if you take the Taylor series, you can see this is the Taylor series. T1 and T2 are given as u I plus 1. I plus 1 is nothing but the succeeding element with respect to the present element I, where ui plus, this is a Taylor series, which generally already you have studied. This is a Taylor series. This is ui minus 1, which we define with respect to the preceding element. So these are the Taylor series elements, where we define Taylor elements on the left and right side, right elements with respect to the present element by using Taylor series. And these are the differentials. This is the second order derivative approximation, and the second one is Taylor series, which we can get from that equation. And again, if you want to define differential dou u by dou t, that is nothing but your velocity with respect to rate of change of velocity, it is delta t will be coming in the denominator, whereas if it is a length, delta x will be coming into the denominator. Similarly, this is for forward difference. That means it is with respect to the succeeding element. In summary, we can see how to discretize, or how to find out, discretize the elements is by using the finite difference method. Is, for example, this is dou u by x. It is with respect to ui plus 1 minus ui minus 1 by 2 delta x. This is nothing but central difference. And this is also a central difference. And in this way, you are going to convert the differential equations into algebraic form for the first order, which is used in finite difference method. Whereas in finite volume method, you go for the mass balance or energy balance or momentum balance. In finite element method, we go for load balance. These are the, you can see this is the figure where you can see this is delta x. Delta x is nothing but, it means whatever the elements we have taken here are equispaced elements. That means the length of the element is fixed. And you can see the x-axis is delta x, and y-axis is u. And here he has explained the central, this is a curve. If you define this with respect to this element, this is with respect to central, this is with respect to, for this curve, this is with respect to forward element, for this curve, this is with respect to backward element. Like this, you can define any you can make the finite differences and finite volume with respect to succeeding and preceding elements based upon the data available. This is again, I have shown the same thing I am repeating here with respect to the time as well as with respect to the size. This is obtained. This is nothing but the Taylor series, and these are very important to understand in order to solve any fundamental research problem. And the same figure is being repeated. Here you can see whatever the conditions we have taken. It is equispaced. It is not unequispaced. So the forward, backward, or central difference is suitable for only equispaced but not unequal spaced. So in order to study or in order to do the analysis where the spacing or the grid is unstructured or unequal space, there we go for Lagrangian 3-point formula. Lagrangian 3-point formula plays an important role where we can have any type of, we can define any type of size, any type of structured grids or unstructured grids, whether the spacing is same or different between the elements. For example, I have given here T of X, that is a temperature, T1, T2, T2. Where you can see the T of X is given as X minus X3 into X minus X2 by X1 minus X3 into X1 minus X2 into T of 1. T of 1 is nothing but the temperature of first element. T of 2 is temperature of second element. T of 3 is temperature of third element. It means the temperature we are defining here is in the forward difference. Similarly, this is also a forward difference. Similarly, we can define the temperature with respect to backward difference as well as central difference. If you define based upon the same equations, if you substitute equispace, that is x1 minus x3 means this is x1, this is x3 minus 2 delta x, x2 minus x3 that is minus delta x, x3 minus x1 that is plus 2 delta x. If you substitute, if you assume that it is an equispaced, then the above equations will turns out to be the same thing, and we are going to get the same equations whichever we have used for forward or backward or central difference. And the basic applications or the general applications of this fundamental research are solar collectors, IC engines, gas-cooled nuclear reactors, measurement of velocity using hot wire anemometer, cooling of electron. This is very important. Cooling of electronic component devices, as well as aircrafts, etc. Now, before going to, I have already told we are going to discuss a simple problems based upon the finite difference and finite volume methods. In the finite difference method, first of all, I am going to discuss 3 different problems. One with respect to a simple one-dimensional problem, second one with respect to two-dimensional problem, and third one with respect to three-dimensional problem. And this is pertaining to the fundamental research. I have already told the first thing is we should define the problem clearly and understand the problem. Otherwise, we cannot solve the problem in this particular cases. For that, I have taken here a simple problem to make you understand the concept of how a fundamental research is going to be performed. Here you can see it is a vertical plate having the length L, and it is having only the heat that is generated is QV watt per meter cube, and the thermal conductivity of the material is assumed to be K watt per meter Kelvin. If the heat is generated, then the heat is generated and is dissipated to the left and right surfaces by convection and convection. we assume that the heat is transferred by convection and conduction, and the plate is having an emissivity epsilon, and we have neglected the y and z directions. If you consider the elements from I is equal to 2 to m, if there are m elements, m minus 1, the heat transfer is due to conduction. And there is heat generation. If we assume that it is a steady state equation and one dimensional, the y, z, and the transient condition dou t by dou small t will be eliminated, and the equation will turn out to be this one. So here this is a one-dimensional plate where the heat is generated and it is exposed to the atmosphere on the left and right surfaces, and it is assumed that the left and right surfaces are exposed to convection and radiation, and the surface of the plate is having emissivity epsilon, and the heat transfer coefficient H is taken as a heat transfer coefficient of the air. Since it is a conduction, the equation, general conduction equation, if you apply from I is equal to 2 to I is equal to m minus 1, this is the equation which we get. And here you can see this is a differential equation. Now our aim is to convert this differential equation into algebraic form, where I have shown the Lagrangian 3-point formula. And here I have used the Lagrangian 3-point formula, and as I assume that it is of equi-space, that is delta x. Then I am going to get the temperature of element I with respect to preceding and succeeding by this equation. And this is QV into delta x squared by 2. This is the equation which we are going to get. By this equation, we can find out the temperature at any point from I is equal to 2 to I is equal to m minus 1. If you consider a left boundary, that is nothing but this is the left boundary which we have taken, that is I is equal to 1. When you consider the left boundary, it is exposed to the atmosphere, that is, it is exposed to, and the heat is transferred due to convection and conduction, the convection and radiation, whereas on the right side it is due to conduction. And you can see it is convection, radiation, on the right side it is conduction. And we take the half element as taken as delta x by 2, and this is the heat that is generated. If you put the energy balance, convection and radiation and conduction are outside, whereas the heat is generated inside, and this is the energy balance which we are going to. And you know the conduction equation is minus k d by x, and the convection HA delta t, and the radiation sigma epsilon T1 power 4 minus T2 power 4. And our variable is T1 or Ti is the one which we need to find out. So the T1 or Ti is found by the government. If you solve this equation, and if you find out, if you substitute dt by dx by using final difference method, you will get, this is the algebraic equation where you can get the temperature on the left surface. Similarly, we can find out, we can apply the energy balance on the right surface also. Once you apply the energy balance on the right surface, you will get a similar equation for Tm. And we got now 3 equations, M equations to solve this problem. And we write a code in C language by using this, and we give the relaxation parameter as full relaxation. That is delta is equal to T nu minus T volt by T nu, which is nothing but the convergence criteria. We have taken this as a convergence. T nu means present, T volt means initialization. So initially we initialize the temperature by either atmospheric temperature or 0 or anything else. But when we use an iterative solver, that is nothing but Gauss-Seidel iterative solver, then automatically, though the number of bits or the number of iterations may increase, but finally you will get the final solution. And the convergence criteria is taken as 10 power minus 6. It means T nu minus T volt by T nu into 10 power 100%, it should be less than or equal to 10 power minus 6. Then only it will go into the program, otherwise it comes out. So in this way, we can get the temperature at any location in the element. If you take, this is an example where we have taken only one directional flow. But in actual conditions, there will be not only one direction, but it is also 3 directions. So, but we are going to take another example that is 2 directions, where you are having a plate having a length L, X direction and Y direction, and it is exposed to the atmosphere on the 4 directions. And the heat is generated. The QV is the watt per meter cube is the heat generated, and K is the thermal conductivity. If you take this into consideration, the inside element, that is I is equal to M2 to M minus 1, J is equal to 2 to N minus 1. That is number of elements both in X and Y directions. If you take these elements, these are with respect to conduction because they are inside the plate. And you know what is the governing equation for conduction in 2 dimensions when it is a steady state condition. And this governing equation is used again, converted into algebraic form to get the temperature at any location. Okay, the similar methodology whichever we have used in the previous case, the same thing we can use here also, but the governing equation changes. As the governing equation changes, naturally the temperature at various locations changes. And this is again similar to right boundary I have taken. In the first case I have taken left boundary, but here I have taken the right boundary as an energy balance. And you can see here if I take the right boundary, the conduction in and conduction out. Conduction in and conduction out. This is the net rate of heat transfer along Y direction, X direction, and this is Y direction. So if you put the energy balance and if you substitute conduction equation minus Ka dou T by dou X, convection equation HA delta T, conduction, net conduction by Fourier conduction equation, and this is radiation. If you substitute all these equations, and if you convert dou T by dou X into algebraic form, then bringing Tij on the left side, this is a governing equation in the form of algebra. And this is the temperature on the right boundary. This is the temperature in the middle. Similarly, you can find out left, top, and bottom also. So till now, whatever we have seen is a 2-dimensional problem and 1-dimensional. Now we are going to come to actual conditions, that is a 3-dimensional, where we apply to conjugate mixed convection heat transfer problems. I have already told finite difference method is used only for 1-dimensional or 2-dimensional components, whereas finite volume is used for all most generalized problems where the solid element, 3-dimensional element, is considered for the study. And here I have taken a conjugate mixed convection. Conjugate means combined conduction, free convection, and forced convection heat transfer. Already you might be knowing there are 3 modes of heat transfer: free convection, conduction, convection, and radiation. Here I am going to take this problem 3 by considering conduction, convection, and radiation into picture. And in the convection also, we are going to consider both the effect of free convection as well as forced convection. That's why we call this as a conjugate mixed convection, that is combined free force. That is, mixed convection is nothing but free combination. It can be a free, partially free, partially forced, or it both may be equal. Okay, what is the parameter that is going to discuss about the free and forced convection? We will discuss in this problem. In order to solve the problem by using finite volume method, I have taken a simple example again, a vertical plate. You might have seen this is a vertical plate having 3 different heat sources. One heat source starting from leading edge, and the second heat source starting from, then we have seen a non-heat source portion, then heat source portion, then non-heat source portion, then heat source portion. I have already defined vertical plate with multiple discrete non-identical heat sources. Means the heat source lengths are non-identical. That is, and I have taken this length of the heat source as LH1, LH2, LH3. And you can see on the left top and bottom surfaces, it is made adiabatic. and the thermal conductivity of the material is taken as Ks, and the white portion is nothing but the non-heat source portion, whereas hatched portion is nothing but the heat source portion. And you can see the total length of the plate is taken as L, and the air is flowing over the surface, and the x direction we are considering in the vertical direction, and g is the acceleration due to gravity. If the air flows over the flat plate, since the heat is generated inside the plate, this heat, whatever is generated, it cannot go on the left or top or bottom, and it only dissipates on the right surfaces. So we have made wantedly adiabatic on left top and bottom surface in order to explain the concept of fluid dynamics on the right surface. I have already told that we need to discuss, we can have a structured grids or unstructured grids. Structured grids can be a uniform grid, always a uniform grids and uniform shape, whereas unstructured grids can have non-uniform size. Here, for this problem, for non-uniform size, we can use finite volume method only by defining or writing our own code and not defining our own problem and implementing ourselves. This is the plate which we have seen just now, and this is, I said that the fluid is flowing over the flat plate. Now I need to discuss the fluid properties over the flat plate. For that, I have taken a domain. I said that the next step, once the grid is formed, we need to decide the domain, computational fluid domain, and the boundary conditions. I've taken the domain here, length L, and also have taken the extended length L. Generally, this particular plate is used in electronic cooling. And here you can see these are the, I've taken I is equal to 1, that is the element 1, and M1 means number of elements in the heat source is M1, number of elements in the heat source 2 is M2 and M3 minus M2, and number of heat source in the heat source is M5 minus M4. Like that I have taken, and you can see the grid size is non-uniform. We have taken a semi-cosine grids, which is not uniform. Means we need to write our own software, we need to generate our own code, we need to do our own analysis to get the results. For that, we need to define our own boundary conditions. These are the boundary conditions which are defined and applied on all the 4 boundaries, both in extended region and plate region. This is called as plate domain, and this is called as extended domain. Based and have taken the coarser grids in the extended domain, whereas finer grids in the plate domain. Here you can see the bottommost plate surface. These are the boundary conditions I have considered. Left plate region, this is the plate region where you need to find out theta, and this is the extended region, and this is the top boundary region of the extended domain, and this is the right region. We have taken uniform grids on x direction and coarser grids, the 2 coarser grids, whereas as we move along y direction, we have taken finer grids nearer to the plate and coarser grids away from the plate. The reason for this is because the effect of heat that is generated in the plate is more nearer to the plate than away from the plate. And you can see these are the uniform grids in x direction, whereas non-uniform semi-cosine grids on y direction, finer grids nearer the plate and coarser grids away from the plate. And we have used a semi-cosine equation to solve this problem. I have already told for each and every grid, you have to impose the boundary conditions and the governing condition. Governing equations. So these are the governing equations which we are imposed on the fluid. That is the continuity equation, which is mass balance. X momentum equation, that is nothing but momentum balance in x direction. Y momentum equation, this is energy balance. Okay, and y momentum is a momentum along y direction and energy balance. So these are 4 equations. These 4 equations are converted into three equations by defining a term called as stream function and vorticity. These are nothing but stream function is given by dou psi dash by dou y is equal to u, dou psi dash by dou x is equal to minus v, and vorticity equation dou v by dou x minus dou u by dou y. Once you substitute these 5 and 6 in 3 and 4, 2 and 3, you will get a non-dimensional vorticity stream function vorticity equation. This is the dimensional stream function vorticity equation, and this is the stream function equation, and this is the energy equation. So the x and y momentum equations are combined to form a single equation. So here we are having omega, psi, and t are the three parameters which were considered as three unknowns, and we need to find out the temperature, stream function, vorticity, which are components of stream function and vorticity are components of velocities along x, y, and z directions. Any mathematical or heat transfer problem, once you define the equations, you need to normalize them. Otherwise, it will not be a general equation. So we have used these parameters to normalize the above equation, that is u is x, capital X is equal to small x by L, y is equal to small y, capital U. These are the normalizing parameters which we have defined to make these equations non-dimensional. And here you can see this is a T minus T infinity by delta T reference. We have defined the delta T reference as QV, that is the heat generated into LH. LH is nothing but the total length of the heat sources, which is given by LH1 plus LH2 plus LH3 into thickness of the plate by thermal conductivity. That is nothing but QV into volume by thermal conductivity. That is nothing but the total heat by thermal conductivity will give the delta T reference. Once we invoke those equations, we'll get the vorticity transport equation. This is the equation where the omega is the vorticity, psi is the stream function. And here we get a term called as RL star, which is nothing but modified Richardson number. I just now told modified Richardson number dictates the type of flow, whether it's a free convection, forced convection, or pure mixed convection. If RL star is equal to 0, 1, it means it is a pure mixed convection. If it is less than 1, it is forced convection, and it is greater than 1, we assume it is a free convection. And this is taken as RL star G beta delta T into L by U infinity square, which is given by Grashoff's number by Reynolds number square. And this is stream function. And here another equation we are going, another energy equation, when you substitute, we get the term called as Beckley number, which is equal to Reynolds number into Prandtl number. These three equations are solved by using finite volume method of Gauss-Mann et al. To get omega, psi, and theta at any point in the fluid volume. So what is that we are going to do is we are going to find out psi, omega, theta at any location within the fluid volume. Once we get governing equation, what is the next step is we should convert this into algebraic form. In order to convert this into algebraic form, directly we can use either finite difference or finite volume method. I have used these for this fluid flow particles. I have used finite volume method of Gauss-Mann et al. Whereas you're having energy plate region, you're having fluid region, plate region. For plate region, again I have used energy balance as we have done in the first case and second case problems. And this is, we can take this as an energy balance of the heat source in a plate. It is adiabatic, convection on the right side, conduction going in, conduction going out, and the heat is generated. If you apply QV into T into delta X, is nothing but the heat, length of the thickness of the wall, length of the plate, in plus QX conduction in is equal to QX conduction out plus Q convection plus Q radiation. Substituting those equations, that is conduction, The Q conduction minus convection is nothing but we can call it as a conduction equation. We apply the conduction equation here, and convection H delta T, and radiation sigma epsilon T into T infinity. Once you substitute all these parameters, you are going to get this equation, and non-dimensional there will get this equation, where IRF is equal to radiation flow interactive parameter, and epsilon zeta is given as thermal conductivity, which is the ratio of Kf into L by Ks into. Kf is nothing but the thermal conductivity of a fluid, Ks is nothing but the thermal conductivity of the surface, G1 and G2. So like this, you can get various equations. The equations we are going to get both in fluid region as well as the governing equation we have got in plate region. Totally, we are going 3 in fluid region and plate region, nearly 9 equations. 9 plus 3 total, 9 plus 3, all the equations are converted into algebraic form. Okay, and a convergence criteria is applied. For example, psi. For psi, sin mu minus psi old by sin mu, which is 1, it should be less than 10 power minus 4. Omega 5 into 10 power minus 4, theta 1 into 10 power 4. This is the convergence criteria I have defined based upon the problem definition. And here I have given full relaxation for the temperature, whereas a 50% relaxation for psi and omega. When you solve this problem, if there is no convergence, we need to change the relaxation parameter. For this particular problem, the relaxation parameter for psi omega was to be 50%. That is T sin mu minus psi old by sin mu. Sin mu will be minus 0.5 psi old. Like that you are going to take. And these are the range of parameters which we have. RL star 0.01 is nothing but forced convection, 250 is nothing but free convection. Epsilon 0.05 is nothing but the lowest bad emitter, 0.85 is the excellent emitter, and thermal conductivity 0.5 to 1. Because whatever the plate we have considered here is nothing but mylar coated epoxy resin, which is used in electronic cooling, whose thermal conductivity is lying between 0.25 to 1. Once we have done this equation, energy balance is done and is validated with the Ramachandran et al. I have already told the grids are directly structured. If the structured grids are there directly, you can use the software. But if it is unstructured grids, which we have defined ourselves, we should do grid sensitivity analysis. If you do not do grid sensitivity analysis, you are not going to get the correct results, and it is not at all validated. So for this, I have done grid sensitive analysis by fixing the number of grids along y direction and varying other parameters in the first stage. Then I have got 151 as the number of grids in a m direction. Now I have fixed the number of grids in y x direction and varied the number of grids in y direction, that is n. And based upon the percentage change, I have found that appropriate number of grids is 91. Similarly, in heat sources also I have fixed other one heat source grids and varied, and I have got the number of grids in fourth combination, that is 41 in say heat source 1, 51 in heat source 3, 2 and 51, 81 in heat source 4, like this. So these are the final number of grids that are being obtained by grid sensitivity analysis. Once the grid sensitivity analysis, here I am going to discuss a simple example. I have studied this, learned the program by taking RL star from 250 to 0.01. 250 means the free convection mode of heat transfer. 0.01 is forced convection mode of heat transfer, for which I have fixed these parameters. That is the heat generated inside the plate, the thermal conductivity, and the surface emissivity. And based upon this study, I have got like this. You can see the heat, the temperature is increasing, reaching maximum and then decreasing, and reaching maximum and then decreasing. This is because of the heat sources available at various locations. Similarly, you might be thinking that the radiation may not be more effective in electronic cooling. In order to explain the concept of radiation or role of radiation, I have taken epsilon is equal to 0 and epsilon is equal to 1, and it is found that the effect of radiation is more In case of electronic cooling, that is the rule is around 30%. Once the data is generated, large amount of data is generated, and the correlations are generated for this particular case. For non-dimensional maximum plate temperature, this is a correlation which we have got for non-dimensional maximum plate temperature. This is a non-dimensional average temperature correlation which we have generated from the data by using Axum software. This is a mean friction coefficient correlation. This is another mean friction coefficient correlation. One is for between RL star for forced convection mode of heat transfer. The other one is for free convection mode of heat transfer. So this is with respect to fundamental research. Still now we have seen only the fundamental research. Now in actual conditions, sometimes we may come across the actual conditions. All of you please see this. Is it audible? Is there any settings are to be performed?
I think here it is not there. Okay, sir, go ahead.
Now is it audible?
I was admitted to the ICU for 4 months, where they had to implant
It is audible.
an
It is audible.
ventricular assist device, and it's considered an artificial. In 2012, I was diagnosed with a cardiomyopathy, which affects the heart's efficiency to pump blood. I was incredibly ill, admitted to the ICU for 4 months, where they had to implant what's called an LVAD, which stands for left ventricular assist device, and it's considered an artificial heart. It's taking over the work of my heart for
I think all of you might have seen this particular video where you can see this is one of the application which we are performing in our institute. That is nothing but analysis of a total artificial heart. This project and design a prototype for having a total artificial heart in our institute in the market. T.S. Reddy, Harvey Borowitz, and James F. Antaki are the 3 crucial people who have been dealing with this project. And coming to our India, we ourselves, Kakatiya Institute of Technology, BITS Pilani, CBIT, Srinidhi, and Laxman Systems are involved in this project. And in not only UPMC, to UPMC, Mississippi State University, okay, and Berlin Hart, and Oklahoma University, Cornell University, etc. All the people are involved in this project. So why you might have considered, you might have thinking why this video was shown, what is the need of this video, how it is related to us. Basically here in total artificial heart, a pump is used, a continuous pump is used to circulate the blood through the body. And you can see that video whichever you have seen is nothing but dictated by the flow pump. Why this is very important? You might have seen this. From this we can say that the heart failure rate is going on increasing drastically from 1960 to till 2020. In order to decrease this heart rate, this project was introduced. And this project was introduced in order to get the product in the market with lower cost and suitable for Indian people. Here, the main reasons for the heart failure is loss of pumping ability, stress, and lifestyle like smoking, being overweight, eating foods, etc. These are the conditions that may lead to heart failure. Artery disease, past heart attack, high blood pressure, abnormal heart valves, heart muscles, heart defects, severe lung disease, diabetes, sleep apnea. And if you see here, just see this video. This is nothing but the pulsating heart function or working function of a heart. We can see on the right side a signal, how the heart signal is produced. It is just pulsating. It is a pulsatile wave that is being induced in order to circulate the blood or in order to pump the blood. So here, in order to pump the blood, we use this component, that is the left ventricular assisted device. In order to pump the blood, I have just now told, there are two types of blood pumping devices. One is pulsating device, the other one is continuous device. These are the two components, axial continuous rotary or reciprocating devices, which we use to pump the element. And this is nothing but for linear displacement and rotary displacement. That is just now I have shown axial flow pump and centrifugal pump. And this is the pump location in the heart. And this is an example for continuous flow device, which we use in our applications, total artificial heart. How this total artificial heart was started in the first generation, and it is initially started in 1970s, and Mr. Jarvik was the first person who has introduced this into the market. And then in the first generation, he has taken it as a pulsating pump. But there was a lot of disadvantages on this, and they proposed to go for continuous pump in the second and third generations. You can see in the first generation, they have used pneumatic power and control multiple moving parts and pulsatile flow technology. In the second generation, they have continuous technology, but contact bearings were used. But these contact bearings are replaced by magnetic levitation bearings. And these are the advantages and limitations of the pulsating flow blood pump. It is very cumbersome. External reliability problems are very large. Fatigue cracks were formed, and the life expectancy was very less than 3 years. So they have started. This is again the first generation pump. They have gone to. This is nothing but a pulsating device which is made by HeartMate. Then in the second generation, continuous flow pumps were used. And the advantage of this is smaller in size or size, better reliability, no requirement for external pneumatic power and control. Whereas in contact bearings, the main problem is contact bearings, which is killing the cells. In third generation, the same as second generation, but the contact bearings are replaced by the magnetic bearings. And the motors, these are the different motors that are used in order to run the pump. Then these are the desirable characteristics. What is the role of mechanical engineer here is to control the fluid flow, to do the analysis of the fluid flow. You can observe that the fluid that is flowing here is nothing but a blood, which is a non-Newtonian fluid, and hence making analysis of a non-Newtonian fluid in CFD, which is nothing but application research. Is nothing but an application research. Is very critical, and this problem is being performed in our institute in collaboration with UPMC. And here we have taken the flow rate as 5 liters per minute and the torque. These are the design parameters we have taken. Based upon the design parameters, we have defined or designed a pump. This is nothing but the floor, 4 blades, and this is a volute with a blade in impellers. And these are the results which we have got. That is nothing but absolute pressure results. This is wall shear. Wall shear plays an important role in this because the blood is a critical component where it loses its cells if the wall shear is more. This is, you can see here the wall shear is more at this location. Effective velocity, viscosity. You know what is a viscosity? And the viscosity effect is more at the exit inlet to the volute region. Heat transfer coefficient, heat flux, vorticity, velocity. And once the design is design and analysis is performed, we can make a prototype in the CAD model and we can design a prototype, and based upon that we can do the comparisons. These are the comparisons which we do, and these are the results which we have obtained. Is the turbulence that is occurring in the blades, pressure contour, velocity contour, wall shear, velocity stationary, pressure contours. And this is the results which we have obtained for 4 and 6 blades. And we have set up the mock-up loop test setup in our lab. And we have tested the pump. These are the test methods. This is the circuit diagram where we have used the lab view. And this is a model of the pump. Thank you for your patience. Thank you once again.
Okay.
And here I'm stopping my session.
Okay, thank you, sir, for valuable session, for your valuable session. You have enlightened about the overview of the computational dynamic in thermal engineering, and finally you are concluding with the heart project and what is the work is carried out in the kids Warangal. It's a really nice, sir. Now I welcoming our participants. If you want to ask any question, you can welcome now. Talk to our presenter. Hello, participants. Any questions, please? Hello.
Unmute just Anand.
Yeah. They can their own. They can unmute.
Yeah. Any questions, if possible, you can ask. Otherwise, we can stop.
Okay, sir. Thank you very much once again. And now I have a small doubt about now how you are validating your this artificial pump, sir. Can you enlighten with your words?
Yeah. Once we have made a simulation analysis,
yeah,
we have to do the experimentation also. The simulation model is manufactured by using 3D printing machine, and the analysis is tested by mock-up loop test setup, which is being installed in our lab. Based upon the mock-up loop test setup, we will validate our simulated model.
Thank you, sir.
Sir, there is a question from the chat box, sir.
Yeah.
Sir, Chettam Shetty Venugopal sir has asked that what are the parameters taken for blood as fluid?
Yeah, we have taken various parameters, but since this is the patent is not yet completed, we are not disclosing those parameters. Please now. Once the patent is filed, we'll definitely answer your question, sir. Please try to understand from our side. Strictly speaking, we cannot speak all those things, but as of now, it is time to discuss. I have discussed only the parameters which are already there in the literature, but the parameters which we consider cannot be discussed now because we need to go. Once the filing is over, we'll definitely answer your question, or we will mail you. You just give your mail ID. Okay, na sir?
Thank you, sir. There are a lot of comments in the chat box, sir. Everybody is uploading your presentation, sir. Thank you very much, sir.
Okay. Any questions? Any further questions are required? Thank you.
Okay, thank you, sir. Once again, we thank you for your presentation. At the
Thank you
last
very much.
minute, you are agreeing, but even it is less time to prepare your preparation. Your preparation is very good, sir. Thank you very much, sir.
Thank you.
Okay, dear participant, our second session feedback will be shared, and it will
Already
be
shared.
it's shared already. So you have to fill within the stipulated time. Okay, and tomorrow's session sharp 10 o'clock we will start, and tomorrow's session will be taken by Dr. Vijay Kumar, and he is assistant professor in NIT Warangal. So you should be ready with it before 10 o'clock. Okay, if anything will be there, and we will share in our WhatsApp group.
Thank you very much, sir.
Yeah.